record this. So before, hello everyone, welcome back again. I hope everyone had a good exam. I posted a solution online on the module, so you can check that after the class. Don't do it right now. And I will bring your papers hopefully by Friday. That's the plan. It's post-slow grading. But then you can pick it up if you want it. If you trust me grading and you don't want to look at the papers, fine. I'll just check them. But they are my responsibilities. I have to keep them for a while. But they'll be busy for a while. All right. So for programming assignment, raise your hand if you're a graduate student. Okay. Now drop your hand if you already signed up in a group. Okay. So if you haven't signed up, so if you're an undergrad that also this course is graduate or count as graduate course for you, you count as a graduate student. All right. Because some of you have the accelerated program. If you go, if you go inside the PHU, so I created two, they are similar. The only difference is I included the list of the students. So let's say you're a graduate student and you're trying to find someone to group with. There is a list here. So for undergraduates, just list of undergraduates from all the major. I put the major also in front of you. I encourage you to group up with someone that's not your major if you're undergrad. For graduates, it's either EC or ME. It's a really good thing matter because you're probably first year. So, for undergraduate student, try to team up with someone that's not your department, so you learn more stuff. Make sure that you are, so once you check the names, you can go to people and then graduates. So when you look at it, you don't see something like this, you see all of them together. So it will be graduates and then at the end will be undergraduates. And try to find groups that there are one student or two students that don't have a teammate. If you couldn't find, tell me. You cannot start your assignment before you have your teammate. What's the point of group work, right? I don't want you to be doing separately because you'll be submitting one assignment. Was there a question? Okay, so the assignment has two parts, right? Part one, you just remember last question of your exam is the same robot of this. So you already have done part of it. You have the solution, so you can check, but you have to continue it. So you found a screw axis, now you have to find bracket S and then find that solution, have to find a 4x4 matrix. You'll do all of that by coding. So the printout of that will be 4x4 matrix. Also, you grab the rotation matrix and the position. From rotation, you can tell me axis angle maybe, representation of that motion compared to the base frame, right? So that will be part one, everything numerical. Part two is the simulation of the same thing. So if you use data from user for the join variable, use the same values in the second part, because we're going to compare how your simulation matches your theoretical solution, right? And then you will say, did it match or not? If not, what do you think happened that it didn't? Sometimes the way you simulate things might affect, all right? It should match, but there are ways that it might not, and it's not your fault. So the robot will be the same. So as a team, we're gonna work together. Now, if one of you already went ahead and did the first part, so I expect everyone to be able to do the first part, it's fine. Just make sure to pick the one that looks good. But the second part, I want you to work together. I want to see a robot that resembles what was in the assignment or in your exam. So it doesn't have to necessarily look like that. You could use lines and dots, circles to simulate the robot, but it has to have motion. And I would suggest to challenge yourself, if especially you're a graduate student, I would expect to see the GUI or GUI, the front end. Right, so you're plugging the numbers and then you see things moving and then the solution is already there. If you haven't used GUI or GUI, there's a link in this assignment that tells you about it. So this is the robot of this question for both parts. If you haven't worked with GUI, you can check this. If you're an undergrad, I don't expect the GUI part yet, unless I specifically told you you have to have the GUI, okay? the goal for you is to be able to learn how to simulate, how to create lines, how to move them, how they all connect to each other. I don't want one arm to move and everything else to stay at one position, right? It has to be smooth transition. So the grading for graduate and undergrad will be different. The expectation is different. For graduate students, you can team up to 3. If you are 2 and you think you're capable, it's fine, doesn't have to be 3. But 3 will give you option. You cannot change your team later. Oh, the assignment is a lot bigger. I need a third person to might help me. Decide right now. Graduate student, you cannot work individually, has to partner with someone. So most of the graduate groups are full. There are a couple left. Make sure that you are with someone. Don't assign yourself to separate groups and just wait forever. But today will be the day that you figure out your groups and then you can work on your assignment. Okay. Make sense? All good? All right. Where's Edmund? That's the second.
He wasn't in my class.
Yeah, he wasn't in the one before the exam either. Okay. You can't be missing too many classes in general. All right. So today's class is short, but probably spicy. It's like me, small, but feisty. Okay. Feisty, I'm not spicy. I'm feisty as anybody can tell you. I fight for everything. Even if there is no problem, I create one and I'll fight for it. All right. So far we talked about 4 kinematics, 2 methods, all in all to find the position and orientation of the end effector. That was the question exam, right? Position XYZ, orientation theta 1, 2, 3 about if you have 3 axes or just 1 axis and 1 theta. So it tells you in which direction your end effector has rotated, okay, with respect to this sphere. Now we're going to talk about velocities. So we are going to develop velocity kinematic expression for the same end effector, right, for the same robot. Now, it's easier in the process because it's just one expression, one simple expression, but since it's a new topic, you might find it a bit more difficult to follow at the beginning, but I'll make sure that you understand how it works. Based on my experience, this is the part that you might have a lot of questions. Don't worry, ask your questions, okay? It has to be clear. By Friday, this has to be clear. Today, if you didn't get everything, wait until Friday, all right? When we were talking about velocity kinematic, forward kinematic, we said that we are using the velocity of the joints, right? So the axis that we found, we said the rotation, that Dr. Z. I'm so sorry. I have to, come on. All right. You know, you have that on that never stop calling you. I love her, but yeah. It's 3 a.m. in Iran. I don't know why she calls me right now. But, okay. All right, so we talked about rotation about an axis. So we found those axes, right? So the exponential coordinate question 4, omega is the axis of rotation. Theta is the amount of rotation. So theta is usually a variable. Omega is the axis that your robot has rotated around. So e to the power of omega t is equal to your rotation matrix about omega and theta. So that's basically what that question was about. But since we already found the rotation, we are going to use that for our velocity kinematics. Before that, we need to discuss Jacobian. How many of you heard about Jacobian? Raise your hand. Okay, good. Oh, more than I expected. All right. So mathematically, Jacobian is taking partial derivative of every variable in a function, okay, against every subfunction in that system. What does it mean? Let's say f of q is your main function and you have n subfunction in it, f1 through fn, right? And your variables are q. So Jacobian says that you have to get the partial derivative of every of those sub-functions with respect to this Q. Now, your variable might also vary from 1 to however many, right? So you might have n variable and you have n sub-function. So we can create an n by n matrix. Okay. So if x was equal to f of q, so x, think of it as output, the solution equal to f or system that has some input, right? Q's are the input. Then x1 would be partial derivative of f1 to q1 plus f1 until qn. So instead of following this sentence format, we just stick to our matrix. And I want you to remember this. So the changes in our output x will be equal to partial derivative of f1 with respect to q1, respect to q2, respect to qn. Then you go to the second function, partial derivative of f2 with respect to the first one, q1, f2 with respect to q2, and f2 with respect to qn. Then you create this matrix. This matrix is called Jacobian and depends on the number of input and output. Input are these Q's, output is this x, right? This could be a vector itself. That is mathematical definition of it. But if you want to think about more of physical interpretation or what really Jacobian does is that it describes how local changes or changes to the input impacts your output. Okay, so for our robot, let's say we have a couple of joints, right? And we are interested to find the velocity of end effector. By now we know end effector is important, right? You're trying to find where the effector ends up. Now, we found the position and orientation previously. Now to find the kinematic, we want to know how the velocity of each joint will impact the velocity of your end effector. Now, if I have m joints, I have to look at m different joints velocity to find out what happens to this end effector, right? So this relationship between each joint's velocity to end effector is called Jacobian. So think of it as mapping like a system that relates the joint variable to end effector variable. Now, since our joint variable changes, you can have different servo motors with different velocity. You can change the PW with different numbers, so your motor will go faster or slower. The system is the same though. Doesn't matter, right? So I can have a slow or fast motor, different rate of rotation or speed, but my system is the same. So the Jacobian stays the same. So we develop one time, that's our matrix, that's a relationship. And then no matter what the input changes, how it changes, we always can find the output. Okay, because we found the system, right? So here, if this is the input, and this is the output of that function that I wrote on top above, we will call this Jacobian. We can write delta x is Jacobian delta q. So I'm showing delta the changes of, right? The changes that happens to the output will be result of Jacobian multiplied by our input. Okay. Now there are different ways of finding Jacobian. This is the direct method. Well, we're gonna first look at the direct method, and then today only direct method, and then Friday I'll introduce two other methods that is related more to our application. All right. So example, you have a function of f from R2 to R2, so two input to output, so two output, so multi-input, multi-output system, right? You could have those. So the output here is two sub-function, f1 and f2. So f of x and y is f1 of x and y and f2 of x and y. What is f1? X squared y, f2 5x plus sine of y, right? It's just random functions. Find the Jacobian matrix. you can use that definition and try to find the Jacobian matrix. So let's identify F1 and F2. We already identified, but let's write it here. F2, 5x plus sine of y. Right? So what would be the Jacobian of this? How would it look like? So partial of F1 with respect to x, our first variable, partial of F1 with respect to our second variable. And if we had more, we'll continue writing. And then partial of F2, so our second subfunction, with respect to our first variable, and F2 with respect to our second. So you should be able to find what this is. Correct? And here, this is partial of F2 with respect to y, not t. So y dot does not appear behind here because it's not function of t. You are getting this derivative with respect to y. So don't get confused with the previous derivative that we had. Okay, so this is the Jacobian. Now let's just give it some number. Let's say our variables were, let's say our x and y, different color, just so you know. So for x, y equal to 1 and 0, find numerical values, numerical value for j. So I can even write it like this. All right, so we found a numerical value. What's the value? Someone
0151.
So what does this mean now? How we can use it? So 0, 1, 5, 0, right? So we can say that
0151.
oh, 5, 1. Cosine of 0 is 1. So we can now say our output in x and y, right? So let's say I'm going to call delta x, so it's x and y. Well, I'm going to say delta f would be this Jacobian 5, 1, and our input on x and y, right? So I can even write it like this, F1 and F2. That's better. So So since we have this information, any changes in our input, we know what the output would look like. So all we did was to just find the mapping between input and output, right? So this is mathematical definition and how it works. Now we will use this in our benefit to find the forward kinematic, and we will use the axis that we already found, the school axis, to find this Jacobian on Friday. Today, we will continue just using this basic method, this mathematical direct method. Now, so definition, right? So now let's go back to our robots. So for differential motion of manipulator, what does it mean? So you are at time 0 at the position, at time 0 plus delta t, you move to a new position, right? We want to know what that position, what that velocity is. We could solve the kinematic from beginning for every single time. So every delta t, we're gonna solve it. Or if we have a velocity, we can always find the position from it, right? So that's why we are developing our velocity kinematic. So let's say that at time delta t, this robotic arm or manipulator system is gonna be here, right? So if this is your end effector, this is going to be also your end effector. I can say from forward kinematic, if I call the position and orientation of end effector x, so x, y, z, theta x, theta y, theta z. Okay, so position and orientation. So from this, from forward kinematic, I know if I have thetas, I can find x, right? If you have the values for theta with forward kinematic expression, you can find the position and orientation of your end effector. Now, this green configuration, we're going to call it instantaneous kinematic. So that is basically for small displacement for a small increment of time. So delta theta can get us delta x, the small move. So we haven't entered dynamic yet. We are assuming this is small enough, and we can find delta theta, and every delta theta will give us delta x. If we include our previous theta, or basically go over time, right? Theta plus delta t, delta theta should give us x plus delta x. So so if we get this rate, will be theta dot, a relationship should give us x dot, right? So something should happen here. A mapping should happen that will get us from joint variable velocities to end effector velocity. This mapping is called Jacobian, right? So if you have the joint velocities for every joint, if you have the relationship, how they affect end effector individually, you would know the end effector velocity. Okay, so this mapping is called Jacobian, or we can use Jacobian for this mapping to get the end effector velocity. We call this expression velocity kinematic. So basically, theta dot is Jacobian x dot. So you see that the expression itself is simple, right? All we need to do is to find Jacobian, and then we already know how many joints we have. So we know all the joint velocities and variables, but we will know what they are. And this x dot is always fixed, right? position, orientation, just the velocity of those. So if I want to write x dot, how does x dot look like? Linear velocities of the end effector and angular velocity of the end effector. So if a robot has 4 joints, like the robot of your example in A2, so you have 4 joint variables, 4 joint velocities, right? They are going to impact the velocity of your end effector. So these are so far easy to follow, right? Hopefully. Okay. So the idea here is to understand what Jacobian is and what's the application in our field. How are we going to use it? All right. We haven't still dived into specific methods of finding Jacobian. This is just mathematical method of finding Jacobian. So if you have a representation of end effector, let's call it x of t, is some function of theta, which we already found in forward chem, 2 different methods. We have expression, right? They're function of theta. We can say that the partial derivative of that function with respect to all the variables is going to give us Jacobian. Still the same definition. And we write x dot of t is j theta theta dot. Here, because theta joint variable changes with time, so that is theta dot, right? Because that theta changes with time. That's hence you can have x dot of t here, because that will be also a function of time. Okay. Now, Jacobian transfers the velocity of end effector transform during velocity to end effector velocity. You will see that sometimes we use theta dot, sometimes we use q dot, all right, to introduce joint variable. You saw before, we could say Q is, you define, here is really how you like to define it. I can say QI is theta I and DI. So if I prefer to use theta for revolute and D for prismatic joint, to put them together, I can introduce QI, my joint variable vector, right? And use Q dot here. So J of Q dot, or if you prefer to just use theta that represent both revolute and prismatic, go ahead. This is your convention. Just make sure to stick with it, be consistent. So this would be revolute. This would be prismatic. I might switch between them, but it's just, so you will see at the beginning, if it was Q, I will introduce what Q is, all right? So since we will have revolute joint and prismatic joint, so for a prismatic joint, what kind of velocity are you expecting? We found the screw axis, right? We expect linear velocity. If we have revolute joint, we could have linear velocity or angular velocity, right? Now, in our Jacobian, we will have also 2 parts that will represent these 2 velocities, and they will appear nicely separated from each other. So they are in one matrix, but the first part, usually the top part, is the linear velocity component, and the bottom part is the angular velocity component. Angular velocity component is always because of revolute joints. Linear velocity could be because of prismatic joint or the effect of the angular velocity. Following still what we said in screw axes and creating that table, finding SI, right? You're still building on that. They're all connected. I will show you how those directly can build this on Friday, which makes everything super easy. So for this example, we're gonna try to find the Jacobian and the velocity kinematic from the direct method, meaning that you're gonna find an expression for, so what's the z-axis? Which direction is the z-axis of, let's say, that first frame? Inside, like outside of the plane, right? So I'm gonna say this is z, x, y. So I'm trying to find the end effector velocity, right? We know that we can find an expression for x and y, right? from trigonometric, so x of n effector, y of n effector. So we're not even using forward kinematic or anything. How do I do that? I have the thetas, I have L1, L2. How would I write what is x?
L1 plus L2.
Yeah, plus. So I'm trying to find this guy, where this position is, right? Yeah. That's what you're thinking. I'm reading your mind. You've seen this before, right? If you open your book, kinematic chapter 4, this is the first example. And we talked about it before. So this is just simple graphical methods, right? Finding x and y. If you have x and y, you can find the velocities, right? That should also give you the velocities. Y of EE, that just is not V, is just y of n effector. That is L1 sine of theta 1 plus L2 sine of theta 1 plus theta 2. Again, these are planar. So if you have planar robots, the easiest way to find their position is probably just using this method. The forward kinematic method that we work, POE and VH table, comes in handy when we have different planes, when we have actual 3D robots, right? So, so this is the simplest case. Now, find the Jacobian matrix for this one. Everyone work on. After this, you will work on your class participation. You have to submit by class time. So start doing this, and then we'll work on class participation. So I'm going to help you a little bit with what Q is. Q is theta 1 and theta 2. We're trying to find Jacobian and velocity kinematic. So another thing I can help you here is f of theta 1 and theta 2 are these two. So you have two subfunctions and you have two joint variable, right? So these are the two input and those are your outputs, your functions. Find J. What is the dimension of this matrix? 2 by 2, 2 input, 2 output, right? So that's the first quick check. Hmm? Oh, it has sign. It's sine. Sorry, it's not cosine. It's sine. You have to get it. Yeah. It's like I wrote it. Why are you telling me it's wrong? Mm, theta 2 cosine of. So this is y getting this sine is cosine, right? And then this one, so I'm working on that. Because I'm doing it in live. So x is, so we're getting x with respect to theta 2 here. So that's the only theta 2. So it's negative L2 sine of theta 1 plus theta 2, right? And then this guy is y with respect to theta 1. So you have theta 1 here. So is L1 cosine of theta 1 plus L2 cosine of theta 1 plus theta 2. And then, yes.
For the Jacobian,
Uh-huh.
the first column be a partial derivative with respect to
Oh, that's why. Yes. Oh my God. Yes, you're right. Good job. Live work is stressful. I'll check my teacher. So F2 with respect to theta 1 and theta 2. Great. All right, now let's do this again. Just read to me what's the solution. So this is theta 2. Okay, we all agree on that one. Okay, so x with respect to theta 2 is negative L2 sine of theta 1 plus theta 2. Okay, now it makes sense. And then let's check this guy. Yeah. So this is L1 cosine, right? L1 cosine of theta 1 plus L2 cosine of theta 1 plus theta 2. Great. And this one is L2 cosine of theta 1 plus theta 2. Beautiful. All right, so this is our Jacobian finally. So what? Well, I skip all of that. If you do it, so theta 1, theta 2 are variables. So I'm going to call it theta 3, right? So because theta 1 is an angle that changes, theta 2 is an angle that changes. So that will be just an angle, right? But if you open up, it has to be the same thing in this back. Yeah, trust me on that one. That one, I'm sure of it. Yes. All right. So what is the velocity kinematic expression? So we found the Jacobian, right? What's the velocity kinematic expression? Ben?
X equals Jacobian times theta.
X or X dot?
X dot equals Jacobian times theta dot.
Okay, so we have two datas. Which one? Q dot, so it's theta dot 1, theta dot 2, right? So, so if you were going to open this, it would have been x dot, y dot, right? Which is Jacobian, that guy, Q, theta dot 1, theta dot 2, right? The velocity of joints will affect the velocity of the end effector, right? Now, your class participation is put some values and find a numerical value for the Jacobian, right? So this is your class participation. For the 2R manipulator, we just worked on find the numerical value for your Jacobian when L1 and L2 are 1 and Q is 0 and pi over 4. That's part 1. Part 2 is to find if there are any values for theta 1 and theta 2 that the Jacobian matrix becomes singular. So that's kind of food for thought. Singularity is configuration that end effector would not be able to reach. There is a mathematical way of finding it using the Jacobian matrix. I want you to think about the physical way of, is there any configuration that the manipulator would not reach the workspace? So your workspace is like a donut, right? So is there a configuration that you will miss 1 degree of freedom, basically? For your question, so when you have
You didn't show the word.
yeah, I can show. Don't look at the book. We just went over this and you should be able to use your knowledge. The idea is not if your class participation is correct or not. If you could understand what happened in the past, right? And you've seen that we were very generous raising class participation. So if you submitted the class participation, you're free to go. That will be the end of today.